Hello, good morning, good afternoon, wherever you are. I would like to know if you can hear me well before getting started. And if you can, I would ask you to write either in the question panel or in the chat panel, just a quick note indicating that you can hear me well. I hope you can. Okay. I don't see any notes. But I hope, okay, thank you. Thank you. I see that you can hear me well now. Okay, so let me, so we get started today with this news about new performance efficiency of the RiverFlow2D and OilFlow2D models with the NVIDIA GPU cards. I think it's very exciting, the performance we are getting with the new version, and I hope that you will appreciate the advantages of that. And so we'll get started right away. Okay, so well, my name is Reynaldo Garcia. I'm the Director of Development and Applications at Hydronia USA and Hydronia Europe. And I have had the help of Nick Calero, who had prepared all the data that I'm going to be sharing with you today regarding the performance benchmarks that we have done with the latest NVIDIA GPU cards. So the outline of today's presentation is as follows. We are going to show some of the capabilities of the RiverFlow2D and OilFlow2D models. For those of you who are not familiar with those models, I will make a short overview of what they can do, what the areas of performance. Then I'm going to present a brief introduction to single processor versus multiple processor computations. What is a CPU? What is a GPU? How they relate to each other in an actual computation, and then I'm going to show you some of the actual results of the RiverFlow2D performance evolution during the last almost 11 years that we have been developing these models. The data that I'm going to show you today relates to the hydrodynamic computations of the models, but also for the first time, we are going to present the performance of the hyper-concentrated flow applications, so non-Newtonian flow applications of the model. And at the end, I will take some time to answer questions that you may have, if you have. In the meantime, if you have any questions, I will invite you to enter those questions on the question panel that you have, the GoToWebinar question panel. And at the end, I will read them for the whole audience and answer them, hopefully then. So first, the RiverFlow2D model that is developed by Hydronia in collaboration with the computational hydraulic a group of the University of Zaragoza in Spain. We have been developing a partnership over the last 11 years that allowed us to take the hydraulic modeling experience to a next level of performance by the use of GPUs. But RiverFlow2D is much more than GPU. It has a large number of capabilities that I'm going to try to summarize in this slide. So the core RiverFlow2D model is a two-dimensional hydrodynamic model that is based on a flexible mesh solution, finite volume solution that includes CPU and GPU. And it's not only a hydrodynamic model, but it's also a hydrologic model that includes rainfall, evaporation, and infiltration. So you can perform simultaneously routing of a flood, but also the actual rainfall and evaporation infiltration processes that may have generated the flood itself. Or you can perform rainfall on mesh simulations on an actual urban area as well. You can add point sources, so the inflows can be from the boundaries, but also from internal point sources. And the model includes features to represent bridges, cover, culverts, gates, weirs inside the mesh, dam breaches, and also the effect of wind on the water surface. So all of this forms what is the core engine of the RiverFlow2D model. Now, in addition, there are what we call modules. These are add-on optional modules that can enhance or extend the performance of the RiverFlow2D to different applications. So for instance, we have the ST module, sediment transport module, that includes suspended sediment transport, bed load sediment transport, erosion and deposition. And we have added recently the option to have bed fraction evolution. So you can model how the different bed fractions that you may have in the river evolve in time and space. And that allows you to simulate phenomena such as armoring, for instance. Then we have the MT modern tailings modules that is quite, it's very much used throughout the world in mining operations, in tailings risk operations, because it's a two-phase non-Newtonian flow model that allows to simulate the tailings breaks and how the flow occurs after tailings dam break occur. So it includes all the capabilities of a non-Newtonian flow model with 8 different formulations for the rheology of such flows. It can account for wet to dry deposits with different material properties that can be added for the dam and the tailings deposit. You can add also water reservoirs and rivers that interact with the tailings flow simultaneously while you perform the actual tailings flow. The model can't account for the pollutant transport that often occur with this type of flows. You can also include dam breach by overtopping and piping, and the inclusion of bed fraction evolution that was also integrated recently into that model. Now there is the urban UD or urban drainage module that integrates the RiverFlow2D with the EPA SWIM. So we have integrated the actual code of the EPA SWIM model into RiverFlow2D, and that allows you to simulate the interaction of the surface water flooding with the storm drain network that can convey the flow through that network and its interaction with the surface, not only from the surface water to the storm drain, but also from storm drain up to the surface water if that can occur. From the environmental point of view, we have two modules, additional modules. That is the PL, pollutant transport module, that simulates advection, dispersion with multiple pollutants and reaction, and also the water quality module that includes the EPA WASP model. And this EPA WASP model, it's included in terms of the conceptual model that has been incorporated into the RiverFlow2D. So the fundamental numerical aspects of the model is that it includes, it's based on a flexible mesh. So a flexible mesh is nothing else than a mesh, computational mesh forms by triangles that you can see here. The triangles can be of different size, but the triangle is the fundamental computational unit. And this is very important for what I'm going to talk in a few minutes about the GPU application. Because at each of these computational units, at each of these triangles, the model computes all of the variables depending on the module that you're using: the depth, velocity, vector in two directions, the bed elevation if you are simulating sediment transport with erosion deposition, the concentration of the pollutants or of the sediment classes that you are considering in a non-Newtonian flow. So all of these variables are solved at the triangle level. And in a standard model or sequential model, this computation would need to be performed sequentially, one after the other, and that's what we have extended with the use of GPU and parallelization. So this flexible mesh allows to perform a wide variety of applications with the model. Since the mesh can be adapted to any geometry, like the ones you see here, like a pier within the river, the mesh can have smaller cells or elements around the feature and then larger cells elsewhere. And that allows the model to attain a level of accuracy that is very important for some applications. You can see here the velocity field around this pier, and you can see this recirculation or eddies that are formed downstream, and also the stagnation point upstream, while you see these high velocity areas at each side of the pier caused by the contraction that it creates. Excuse me. So this type of detail applications is one of the key features of the model. But of course, you can have all kinds of applications, and what I'm going to show you here is a large-scale application that we did for the Inter-American Development Bank in the city of Carmelo Peralta in Paraguay, in South America. And the idea of applying the model here was to design some levees that would contain the flooding that occurs annually, almost annually, at the city of Carmelo Peralta and the internal island that is in front of the city here. So this is the Paraguay River, and the Paraguay River floods almost annually and affects large parts of the Carmelo Peralta population here. So what we did was to experiment with the design of some levees that would contain or avoid the flooding of the main areas of the city and also the island in front of it. And what we're going to see here is the animation of the flood simulation for one of the scenarios. So the colors indicate here, the darker colors indicate the larger depth of flow, and lighter colors is shallower. So what you see on the left is the situation now, where large parts of the sea and the island gets flooded. And what you see on the right is a simulation with the pre-designed levees, where you can see that the levees contain most of the flooding on the important parts of the city here. So this is one typical application of the model that is very straightforward to make. And so after developing the mesh and adding the boundary conditions is very straightforward to perform such simulations. So the other area of modeling that we have is the oil spill area that we cover with the OilFlow2D model. So the OilFlow2D model has also a core, but then it has two main modules that are often utilized. So the main core is the OilFlow2D. It's a two-dimensional viscous fluid hydrodynamics. So it's similar to the RiverFlow2D model, but in this case, it considers the variable viscosity of and density of the fluids. It's also based on flexible mesh. It considers also applications in CPU and GPU, as we'll see. It has the option to use point sources, rainfall evaporation, hydraulic structures, and wind. The overland component includes evaporation, infiltration, and rainfall, hydraulic structures, and in this case, considering the effects of the viscosity of oil or any other viscous fluid, it can consider the heat transfer from the oil to the environment, which is important in many oils because the heat transfer, what causes is changes in the properties of the oil, such as viscosity and density, and in turn that affects the flow behavior that the oil exhibits on the terrain surface. So in this case, the fluid properties vary with temperature. And we had recently also added the oil pipeline module. The oil pipeline modules allows you to simulate literally thousands of oil pipeline simulations for risk assessments in the overland flow model. So it's a very interesting model to consider when having to model a large number of simulations along a pipeline. The oil and water spill model uses the oil trajectory computation by particle tracking. It also considers evaporation, emulsification, and dissolution. But in this case, the model, the particle tracking or oil tracking occurs over a simulation of a water flow. So in this case, you need to perform the water flow in the river or in the coastal area. And on top of that, you consider the oil trajectory by particle tracking with evaporation, emulsification, dissolution, and shore interaction. We are presently now testing containment booms that is important for mitigation or avoiding the knowing where to put the booms that would avoid the oil to get to some sensitive areas. And so this is it's very interesting because you can use this to pre-design where the booms are going to be located for a specific risk assessments or planning, emergency planning operation. This is an application of the oil flow overland flow model. And this is a tank spill. So we have here a tank that burst at some point. and the oil start flowing. What you see here, the colors indicate the water, the oil depth. And I'm going to repeat the slide so you can see the difference. So what we are looking at here is a 2-hour simulation after the oil tank is break occurred. But you see here two environmental conditions are quite different. One is a wind speed of 2 meters per second, and the second one is a 20 meters per second wind speed. So what happens is that the heat transfer, the use of the heat transfer component, the soil cools down much quicker than was initially heated here within the tank, and that rapid cooling lead to a high increase or rapid increase in the viscosity and the yield stress of that particular fluid. And then that high viscosity tends to make it stop at some point during the simulation. So so this is the animation again. You can see here that with 2 meters per second, the runout distance of the oil is much larger than in the 20 meters per second due to that increase in viscosity and yield stress. This is an example animation of the application of the OilFlow2D in the Magdalena River in Colombia. We have several results. Unfortunately, this oil spill area is very sensitive, and we are not allowed to share some results we have from other projects. But this one we do because it's just an illustrative application of the model. It's not a real project that we did for a company or something. It's something that we use to illustrate the use of the oil spills on water model. So we first simulate the water flow along the Magdalena River. This is the city of Barranquilla in the north of the country of Colombia. And so what we see here is the spill that occurs for a certain duration, and how the spill particles or oil particles move along this reach of the river, and some of them are getting trapped on this area of this margin of the river here in the city. Now the model has a very comprehensive user interface that is based on the QGIS system. The QGIS is a geographical information system. It's an open source system that is programmable via Python or C++ languages. It's extensible by because it allows creation of plugins, so third-party plugins, and it's free. So although the RiverFlow2D and OilFlow2D are not free models, the user interface, it is free. And that allows you to install many instances of this interface and just require the license of the model to perform the simulation. So this plugin that we have developed for the QGIS system, it's installed together with the license of the model, and it has capabilities to develop the mesh, automatically adjustment of the mesh, including break lines, integration with digital elevation models. It allows for mapping, has a lot of mapping capabilities for develop maps for depth, velocities, flood arrival times, flood direction, hazard levels, pollutant concentration, material properties. And it also allows for the creation of animation. That's all of the animations that you have seen have been created with the QGIS animation plugin. You can also extract profiles and cross sections from the results of the model. And last year we added the damage cost assessment plugin for the RiverFlow2D model, the HEF, or hydroeconomic evaluation of flood damage. And by having with this tool, by having a simulation of a flood in an urban area, for instance, and a vulnerability database assigned to each of the buildings on that area, you can develop maps that indicates the cost of the flooding for each scenario. So all of this is part of the QGIS plugin. Now, given that the model requires computing the solution at each cell, and the solution involves the solving this set of equations that I'm not going to detail here, but it's a large number of equations because they include the mass conservation of or continuity equation, the momentum equations in x and y, the mass conservation for each fraction if you are using the MT or sediment transfer model, bed erosion deposition, and so forth. So you have, in summary, a large number of unknowns at each triangle, like depth, velocity, two components of the velocity, one concentration for each sediment class, the bed elevation, and so forth. So each of these variables need to be solved. This equation needs to be solved at the cell level and at the edge level. So there is a lot of computation involved in the finite volume method. I think I didn't mention, but it's very important to mention that the numerical method that we use to solve these equations is a type of finite volume method that assumes that each triangle is like a control volume, and then we solve the equations at the control volume level of each triangle, and that is a purely sequential computation, but that can be parallelized, and that's the importance of the appearance of the GPU options. Now, the challenges that are involved in these computations is that the computational meshes commonly involve millions of elements or cells, and this occurs because every time we need to have a higher resolution or large areas that need to be covered, like here in this urban area, or here this is Biscayne Bay in South Florida in the United States. It's about 100-kilometer long bay or coastal area, and what you see here is the animation of the salinity within the bay based on the interaction of groundwater from the inland and also the salinity incoming from the ocean. Now, typically these computations require simulations of 1 year and sometimes longer. So if you have a slow model, that may require a very long time. So improving the speed of the model is critical in those situations. There are also situations where you need to speed up models, like multiple scenarios in oil spills. In many cases, you need to solve thousands of spills in risk assessments. In a oil pipeline, sometimes you have to have spills every, say, 30 meters or 100 meters. And if you have a 1,000-kilometer pipeline, then you can imagine the thousands of scenarios that would need to be performed there. So these are all challenges of the numerical computation. So what is the problem with, let's say, older sequential models that perform one instruction at a time or one computation at a time? Well, the problem is that the speed at which the single processor perform a computation has been stagnant for over more than probably 10 or 15 years. And these graphics show the data that has been compiled that shows, for instance, here the speed or frequency of the clock of the processors in modern day computers from the 80s to the 2020. And I would like to point you to these green data points here that show the speed of this or frequency of these processors. And as you can see here, from 2005 or so, even though from the 80s to 2005, the speed of the processors was continuously increasing in time, after 2005, this speed has stopped increasing anymore. So I well remember the time where you needed more speed in your computations, and you were able to get a new computer. That computer was much faster than the previous one, and then your computations automatically were being much faster. That is not occurring anymore. So there is no way to increase the speed of the computations by getting a new computer anymore, because the speed of the new computers is not getting any better. What is getting better is the number of processors or logical cores. You can see here that from more or less the same period, the number of cores have been steadily increasing. So this points directly to the solution to the problem. How can we make the models run faster? The way to run faster is to make the models able to take advantage of multiple processors, because that's the only way we have at hand with the new computers. So the solution to the problem, or to the speed up or runtime sluggishness of old computer codes, is to parallelize the code, which means to make the code or the program able to take advantage of multiple processors. Instead of computing one processor at a time, then compute simultaneously in parallel in time the computation in the multiple core architecture that we have available now. So the code parallelizations involve executing the model code, the program, in parallel. Okay, one big clarification here. It is not sufficient to bring an existing code and run it in a multiple core computer. You need to recode or reprogram your model in order to take advantage of this. This is not an automatic process as it was before, that you just bought a new computer, a faster computer, and then the model automatically would run faster. That is not the case. You need to reprogram, recode your model in order to the model to take advantage of the new architecture. So in this way, you can make a program. The different cell groups are solved by different processors. So you distribute the load of the computation and make the model run simultaneously in all the cores that are available. Now, which options are available also to perform this kind of coding? You have first OpenMP, which is called shared memory architecture. In this shared memory architecture, you have multiple CPUs or multiple cores with a shared memory area. So the area that is used by the model to store the data is common to all the cores. and that is relatively simple to program. The other option is MPI, which was even an older method. It's called a multiple message passing information between cores. But in this case, the processors and the memory is independent. So you have multiple processors. It's like having multiple computers interconnected with each other, so that you have to transfer information from one computer to the other because the memory is not shared. And then we have the graphic processing units. So the graphic processing units, or GPUs, use specific languages like CUDA or OpenCL. CUDA is a language developed by NVIDIA, and OpenCL is an open source computer program that allows you to bring your code into these architectures of GPUs. So this is the path that we have followed, because it's the one that allows you to be more productive with today's hardware. Now, there are many challenges involved in code parallelization, because the model created before the 90s, for the most part, were virtually impossible to parallelize, because they were created with serial processors in mind, and they often have what is called the spaghetti code. Spaghetti code is a code that is almost impossible to parallelize, because the flow of information within the code is very entangled. It's entangled like a spaghetti, and it's very difficult to understand and bring to the parallel architecture that these accelerations require. So if you are just using a CPU or a computational processing unit, that is what you have available in most computers nowadays, you can use OpenMP, for instance, parallelize the code, but the number of cores or processors is often limited. You have 2, 4, 16, you have today's 32 or even 64, but in that order. And one of the problems of OpenMP is that does not scale well. So that means that if you use 2 cores, you don't get the double of performance. So if you use 4 cores, you don't get the 4 times the performance. So it's not as efficient as we would like. And then if you choose the graphic processing units or GPU path, it's much more. I mean, the options that you have are much better for improving the performance. Now, the thing is that the graphic processing units, as its name implies, were originally designed to accelerate the creation of images or rendering the images in your computer display. That's what the main purpose of it was. So you have a large number of cores that nowadays is maybe larger than 10,000, as we will see. And it's readily available in almost every computer. So every computer has a GPU card or a video card. This video card may have thousands of cores, or at least a few hundred of them in the very low performance cards. And this is a potential use for computation, not only for the video card, for the video performance, but also for computation. And that is what the CUDA option offers. So you can program your model to run not in the CPU as it was originally designed, but to run in the GPU and take advantage of the thousands of processors that are available there. So that in almost any any GPU card. Now, unlike the CPUs, the GPU emphasize executing many concurrent threads that are slow, but they are so many that the overall performance of the simulation is overwhelmingly higher than in the CPUs. So that is the main advantage. Now we, in our models, use the NVIDIA, the CUDA option because it's the widely available one, and the computer language is very, it's embedded within the languages that we use, such as C and C++. Now this table shows some NVIDIA graphic processing units, or GPUs, that we have used over the last 10 or 12 years. What you see here is on the top, different cards. These are cards of different specs. For instance, here in 2014, we had cards that had like between 2,000 and 5,000 cores with 24 gigabytes of memory. This is a professional high-end card that was very costly originally. Now you can get it for a few bucks if you, in the used market. It's a very good card, but it has been surpassed greatly by other cards. Now in the 2017, we had the GTX 1080 Ti, for instance, with 3,500 processors and 11 gigabytes of memory. And so forth, the Teslas. Now this Tesla has nothing to do with the Tesla cars, just in case someone asks. These are all NVIDIA cards. But the Teslas are the high-end cards, and the RTX and GTX are the consumer type of cards, and much cheaper. Now I want to focus on the latest generations, the RTX 3090 and 4090. As you can see here, we now have available processors, 10,000 or 16,000 processors. Now this very same computer I'm using presently has a RTX 4090 card with 16,000 processors, 24 gigabytes of memory, and it has, as you can see here, it has increased in price from the time it appears. So if you can't find one, you may find it, but for this amount. Now the reason that these cards are increasing in price is that because they are used for AI applications and Bitcoin applications. So they are in high demand, and of course, in our case, we use it for numerical computation, but they are used for many other purposes. I'm going to show you results for all of these cards today. Now the RTX, one interesting data from the RTX 4090, this card has 76 billion transistors. That means 76,000 millions of transistors. That is an incredible amount of computational power that you have inside of a card such as this one. Just before starting this webinar today, I just finalized a computation of a full city in Central America, the city of La Ceiba, with a high resolution mesh in less than 20 minutes with a card such as this 4090. So this is something that puts the model applications at a very, very high performance level. Now, you don't really need to purchase these cards if you don't have the budget for it. You can use the cloud service, and then like if you use, for instance, Google or Amazon Cloud, you can create a virtual machine with a top of the line Tesla GPU hardware, and then pay per use. So you pay sometimes less than $2 per hour of use of these cards. So what you do is you create a virtual machine, you create an account, say in Google Cloud, you create a virtual machine with the specifications you want, say a Tesla A100 card, and then uh, bring your model there, just make the installation of your model in the cloud, in the virtual machine, and make all your computations there. And then when your computations are done, you download your results and then finalize the post-processing of your model in your computer. So this is a big advantage of GPUs, that you can use the cloud services and you don't need to have a very costly Tesla card in your computer. Now, how does the CPU and GPU thing work? So this is a general scheme of a CPU, what is a multiple core computer. These are internal cores of your computer and the memory. And this is how it would look, the GPU in the schematic form. So the GPU has a large number of cores represented by these rectangles here. You have a device memory, which is the device of the GPU. And then you have a way to communicate from the memory of the CPU here to the device memory or the device of the GPU here. So what you normally do, you start your computation in the CPU, which is this one, then move your data to the host memory. From the host memory, the program will move that information to the device memory, perform the computation at the GPU level. Once the computation is done, then it's returned, copied all the results to the host memory and back to the CPU, where you can then visualize the results and create maps and all of that. So when you are using GPU, you have to be aware that all of your data needs to be moved to the device memory. So you have to have a sufficiently memory on the GPU in order to be able to perform the simulations on the GPU level. Now, getting that process right is not an easy task at all. In the particular situation of the RiverFlow2D model and the OilFlow2D model, we had to partner with University of Zaragoza to be able to optimize this process, because when it's optimized, it works very well. But if it's not optimized, the results are less than desirable. So you can imagine the amount of operations that need to be performed between the GPU and CPU, and how to organize the cells and the sites of the cells in all of this computation to make it right. Because the thing is that since the computations are in parallel, there are things that are performed at different times and not synchronized between the cores. So you have to synchronize correctly, wait until all of the cores are finalized in order to gather and compile the results to the next time step and so forth. Now, let me share with you some performance tests that we have done with hydrodynamic applications. We have a full document that summarizes all of these results. I'm going to show you a couple of them here only. Now, in the RiverFlow2D model and the OilFlow2D model, it's very simple. If you have an NVIDIA card, it's very simple to switch to GPU model. So you can have you can make your run in CPU or in GPU. And if you're running in GPU, if you have several cards, you can select your GPU card with this drop-down list. You can see here, this particular computer has an RTX 3090. And then you, of course, you select all the options that you may want here, and then perform the simulation with the GPU if that is available there. Now, of course, I need to clarify that the options that are available for the RiverFlow2D model are only those that use NVIDIA cards. If you use an ATI cards or another Intel card, that is not possible to use with the RiverFlow2D model. Now, the performance evolution of the RiverFlow2D over the last years have been, more than incredible, I would say. I had to confess that the first time that I saw the model working in 2013, the GPU model, I was totally overwhelmed because initially my first reaction was to distrust the results because I couldn't believe that a model could run that fast in a parallel environment. So this particular test showed this evolution over the years. So this test is a very simple, short river reach. It's a green river in the United States. It was run with 3 different meshes, 90,000, 19,000, 154,000, and 1.8 million element or cell meshes in order to test the performance of how fast it will accelerate by using different CPUs. Now but let's say the original run is by using only one core, so no parallelization. This is what you would get if you are using a model with no parallelization at all. So this mesh takes about 8 minutes and 14 seconds. So this is in the format days, minutes, days, hours, minutes, and seconds. So this is 3 hours, 23 minutes, 47 seconds. This is 8 days, 23 hours and 17 minutes and 47 seconds. So this 1.8 million cells would take almost 9 days to run with a one core. Obviously, it's completely impractical to do that. So that was in 2013. Now, when we introduced the first GPU, we were able to reduce the time, almost 9 days, to 4 hours, which was something completely, to say the least, difficult to believe at that time, but it was real. Okay. Now, of course, the lighter meshes, the smaller meshes, would take only a few seconds. So from minutes you get seconds, from hours you get minutes, and from days you get hours. That's the typical improvement in time that you can expect. Now, in 1 year later, in 2016, with the Tesla K20, we will still we're able to reduce times for half of that, almost 2 hours. 2018, less than 2 hours. In 2019, half an hour. Now in 2024, with a Tesla A1000, we are in 30 minutes. So bear in mind, just a few years back, we were just able to run this in 9 days. Now we can run it, the same model, in 30 minutes. Now, all of these are high-end NVIDIA Tesla GPUs. So in summary, with these cards, and particularly with the Tesla A100, now we do not own a Tesla A100. We have used the Tesla A100 in the cloud. Okay, this is a very expensive card that we don't own, but we are able to use it and perform these simulations in a very short time. Now, the performance acceleration we are talking about now is about almost 1,000 times. So this is 1,000 times faster than what we were able to use if we are going to use a one-core non-parallelized code. Now, what happens with what the so-called consumer or gaming NVIDIA cards? These are, bear in mind, these are cards mainly directed to the game environment, the gamers, people who need fast graphics. Okay, so it's just that we use it for computation or more serious computation. Oh, sorry. Okay, so what we see here, the same case, yes, that required almost 9 days for the 1.8 million cells. Now in 2013, we were down to 2 hours and 41 minutes. In 2015, less than 2 hours with a Titan Black. This is a GTX card. Now GTX 1080 Ti, almost 1 hour. Less, almost just not too much difference between the 1080 and 1080 and 2080 Ti. Now in the 2019 with the 3090, we are down to 45 minutes and down to 24 minutes with an RTX 4090. Now, the very expensive A100, remember, it was 30 minutes. But with this card, which is much affordable, we are now in 24 minutes. That means 500 times acceleration with this RTX 4090. Now, I have to also to clarify that these accelerations include not only the change in hardware, but also improvements and optimizations in the computational model, in the code that forms the RiverFlow2D and OilFlow2D models. So we are at the same time that we are taking advantage of new hardware, we are also developing and improving the code so that it will be more efficient to take advantage of these new architectures. Now, this previous test was related to the applications of the RiverFlow2D model in a purely hydrodynamic application. I'm going to talk now about the performance in hyper-concentrated flow applications. Now, the difference is that in the hydrodynamic application, the shallow water equations are solved for depth and velocity vector, while the hyper-concentrated flow applications are solved for depth, velocity, and the concentration for each of the materials that you consider. That may be any number, in this case 6 materials in the test that I'm going to show you, and also the change in depth. So there's a lot more computation going on in a hyper concentrated flow application. Now the example that I will show you is the Corrego de Feial dam break in Brazil, what is called the Brumadinho Dam. So what you see on the left is the video from the actual event, and what you see on the right, it's not exactly but the same spot, but it's the numerical computation, the 3D representation of the numerical computation of the same event. So we have done a lot of simulations testing for this, and actually we have been able to replicate numerically what occurred in the Correo de Fayao dam break in 2019. This other video shows the coming from the tailings in the dam and the interaction with the Paraubeba River downstream here that was blocked by the event and eventually was washed out again by the river. So initially the tailings came to the river, were able to block the river, and then eventually the river eroded back the material so that it could find its way downstream again. So all of this is performed by the model and in the particular test that we are going to show you here. So the test was performed with the Tesla 4090. Actually, was also with the 3090. This is the model window, and as you can see here, it was done by with different meshes, 19,000, 150,000, and 1 million cells, with only one core, and then with the GTX 1080, 3090, and 4090. As you can see here, with a single core, 1 million cells took about 4 days and 4 hours. With the 4090, it takes half an hour. That's 181 times faster than with the one core. And you can see here that the accelerations, it's always higher for the large number of cells, and also, of course, with a larger. So acceleration is for smaller number of cells, let's say 20,000 range, is between 60 times faster and 38 times faster, which is a big thing. But you know, the problem is that once you get used to this 100 and 1,000 times faster models, then you get spoiled with that, and you want more and more. Okay, but this is the performance gain that you may expect from this model. So you can see here that minutes are turned into seconds, hours are turned into minutes, and days are turned into hours, and sometimes minutes, as in this case. So this is a big thing, because now you can have many more scenarios to analyze, because you will have more time to make this the performance, because they take so little. And or you can use high resolution models to perform a better accuracy simulations. Now, some final comments is that we think that the remarkable performance of the RiverFlow2D GPU has several implications. First, that computer runtimes are reduced from days to hours, or hours to minutes, and minutes to seconds. And you know, not only that, this allows to make practical some applications that were completely impossible a few days or a few years back, but that it allows you to do much more than was possible before. Also, now you have the option to evaluate larger river reaches. We have users analyzing hundreds of kilometers of a river. Let's say in Brazil, we have a user that applied the model for 600 kilometers. In the United States, in the Red River, 660 kilometers of the Red River of the North between South Dakota, North Dakota, and into Canada. So this is something that is really possible nowadays. The use of GPU technology developed in the RiverFlow2D code also allows using models with larger resolution meshes involve millions of cells. So we have now 8 million cells problems that are even impossible before. The emergence of pay-per-use cloud services such as Google Cloud, where the P100, V100, and A100 cards are available at attractive costs, facilitates the use of the model without having to spend a lot of money. And something important is because sometimes you need to have the card in your computer, and maybe you cannot afford a Tesla 100, or you don't want to have the inconveniences of having to have a cloud service and moving up and down all the information in the cloud. So even the Tesla A100 is the obvious winner in these performance tests. Cards such as the NVIDIA RTX, which are much cheaper to get, and has enough memory, a large amount of memory, make these operations very affordable for the use in desktop options. Now, Hydronia plans releasing along 2024 a new version of the model that will even improve these performance benchmarks. And with the University of Zaragoza, we are having an option that will not require the graphics that you get now for the monitoring of the model run. So they will run in batch mode, and this batch mode, you don't need to output so many graphics that are done with the CPU, and that will increase the performance even more than what you saw today. So that's what I had to show you today. I'll be glad to answer one or two questions if you have. So let's see if I have questions here in the question panel. Okay, so so I have a question here by Mark. Mark asks if this GPU options are available in the present version. Yeah, of course, yes. The model versions include all of the model versions. We don't sell the GPU separately. I mean, this is an integral part of the model. The model runs in CPU or in GPU. So once you have a license, then you get directly the option to run in GPU mode. So that's something that is available for all the modules actually. Okay, I have a questions here. I would like to know the criteria to choose the model, or Hydrobit. Okay, yes, they are asking about Hydrobit. There is, besides RiverFlow2D, there is a model that is called the Hydrobit. Hydrobit Flood is nothing else than RiverFlow2D, but branded through the Inter-American Development Bank for their projects. So this Hydrobit is the same, has the same features as the commercial model, or almost all of the features, but it's distributed through the Inter-American Development Bank. What is the advantage? Well, that is free to anybody that has the relationship with the bank through either through a project or to any collaboration or cooperation, technical cooperation. Normally is given to non-for-profit government or government agencies. If you want to explore that option, just drop me an email to one of the emails here, and I will glad to put you in contact with the person at the Inter-American Development Bank and make the request. Okay, I have a question here. Using an external drive to store the model data decreases the GPU performance? Yes, it does. Actually, if you have a short output interval, the performance loss is higher. So if you have a output interval, let's say you're modeling 24-hour simulation, and the output interval is 1 hour, that's not a big issue because you have only 24. So every time that the model needs to output results, it needs to come down from the GPU to the CPU, because the CPU is the one in charge to communicate with the hard drives or any output device. So if your output interval is very frequent, if you have a frequent output interval, every time that the model needs to output for that interval, it needs to go to the CPU, and that slows down the computation. The new 2024 version, the one I was referring to, that is even faster than this one, is available. All the data that I have presented today is with the most recent version. Is just available. The one that I was announcing for 2024 that is even faster, it's planned for this summer. So during summer, we'll probably have this new version. I have a question here about the turbulence, how turbulence are considered. Well, there are several parameterization. We don't have a specific turbulence model per se. So there are parameterizations about the turbulence flow. In the case of tailings, we have several rheological formulations or friction formulations, and some of them include specific terms for the turbulence computations. I will need to go into the details. If you are interested, I can send you or you can download the trial version from our website, and in the trial version you will have the reference manual. In the reference manual you have a detail of all of the formulations specifically for the tailings or the MT module that include all of the of details about the friction formulations that include turbulence there. Okay, so well, I need to close the meeting for today. I want to thank you very much for the attendance, and also in the future, because this will be posted on our YouTube channel. So if you are listening in the YouTube channel, yeah, thank you also for your interest. So well, until next time, thank you very much. Bye-bye.